Good morning, Chem 2 students. Mr. Keister here with you again today. This is the video for Thursday, September 24th, 2020, which is our scheduled 25th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's look at our do-nows, today's schedule. Today you're going to pick up Lab 2.2 over nuclear spectrometry. Yesterday I handed out the Unit 2.2 review. We have a test coming up on Monday, so you should already be working on that. Your homework for today was to finish the radioactive decay assignment. That is now due. If you're here in class, of course, that should already be on my desk by the time the tardy bell rang. If you're at home, you need to submit that to me electronically by the time your class period begins. Make sure you do that. Of course, the answer keys are posted here on the board. They are also posted on Canvas on my answer keys page. Both of those were done by 7 a.m. this morning. So today we're going to work on Lab 2.2 over nuclear spectrometry. Normally, we borrow our equipment from Purdue and do the lab, of course, here live like you normally would. However, this year with the situation with COVID-19, Purdue has temporarily suspended that equipment borrowing program. And so instead, we are doing an online version of this lab. So whether you're here in class or you're at home, regardless of that, we're going to be doing the lab online, or I should say you are going to be doing the lab online. So if you're here in school, we'll probably gather your lab groups back at the lab table, and you can do that together back there. If you're at home, of course, you can do it from home at your dining room table or at your desk or whatever. So let's see, as far as tomorrow goes, you are to continue working on the Unit 2.2 review. We do have an exam coming up on Monday that covers both Unit 2.1 and 2.2. It's a combined Unit 2 exam. The study list is now posted in Canvas, and I'll put it up on the board tomorrow. You also have a Mastering Chemistry assignment that is due tomorrow morning at 7:30. Don't forget about that. That's Unit 2.2 Nuclear Chemistry. So make sure you remember to get that finished if you haven't already. Okay, so one thing about this lab before I pull it up on the board, it is an online lab, so you guys will be doing it yourselves. I'm going to help you get it started, and so you can see how it works and what it's all about. And then I will break away and let you finish the rest of it yourself, okay? That lab I am collecting tomorrow by the end of class. So for some reason, if you don't get it done during class today, if we're here, or don't get it done from home, you will be able to finish it tomorrow. I am collecting it by the end of the period tomorrow. So, and then of course, the rest of the time tomorrow would be spent finishing up your Unit 2.2 review. So that's the way things are going to go. So let me go over to my desktop and pull the lab up for you. Okay. So I'm going to talk from over there most of the time. I'll come back to the board occasionally, but you'll still be able to hear my voice, and we'll work it that way. So I'll be right back. Okay, so here's the lab paper. Lab 2.2, Nuclear Spectrometry, online version. I do want to read through this with you, so I want you to understand how the equipment works, okay? If it was here, of course, I'd have been doing this from there, but I want to go through it with you anyway so that you see what we're doing. So the nuclei of most atoms are stable, and under ordinary circumstances, stable nuclei don't undergo any type of change. The nuclei of other atoms, though, radioactive ones, are unstable. And remember, nearly all elements have at least one isotope that's radioactive. Most of them do, all right? These nuclei, and even the ones within our bodies, you know, we've talked about this in class. We ourselves are emanating some background radiation because we have elements that are found in our bodies that have radioactive isotopes, one of which, of course, is carbon-14. So, you know, we are radioactive ourselves. Okay. So these nuclei undergo change spontaneously, that is, without outside help. When an unstable nuclei undergoes change, they give off radiation and energy. Radioactive atoms which have unstable nuclei are called radioisotopes. Talked about that in the notes. The change that an unstable nucleus undergoes is called disintegration or decay. Normally we call it radioactive decay. When an unstable nuclei disintegrates or decays, certain particles, alpha, beta, positron, or particles of energy, I should say, and or particles of pure energy, which are gamma, are emitted. So atoms and molecules in the path of radiation are ionized. That is, they are stripped of electrons. That means alpha particles, beta particles, gamma radiation, and other nuclear emissions have enough energy to remove electrons from atoms or molecules with which they collide. Positively charged particles and free electrons are left behind after this collision. Devices that are used to detect radioactivity are based on the ionizing ability of radiation. One such device is the Geiger-Müller tube, which is connected to a counter and is commonly referred to as a nuclear scalar. All right. When a charged particle or gamma radiation enters the nuclear scalar, it ionizes many of the argon gas atoms that are found in the Geiger-Müller tube. The electrons are attracted to the positive side of that tube. It's called the anode. And the positive argon ions are attracted to the negative side or the cathode. This produces a surge of current, which is then counted by the scalar. So that's how they work. And like I said, whether you were here and we had the Geiger-Müller tubes here with us, or since we're doing it online, you'll see that they work the exact same way. Okay. So we will be using the virtual online lab at this address. So I'm going to go pull it up right now. And of course, you can do that either you're here in class, doing it here, or at home. So go on there and hit Control click, and there it is. All right. So as I scroll down a little bit, this is a Geiger-Müller tube here. It's got some adjustments on it that, of course, we don't have to deal with since we're not doing it live. The counter display is right here. All right. And then there's a wire here that leads to the Geiger-Müller tube. Now, normally it's encased in a little plastic or hard plastic case. And then this entire contraption here is within a metal box. But we're showing it so you can actually see it. So we slide in our radiation source here. The Geiger-Müller tube is right here. The radiation emanates upward from the radiation source. They're usually in the form of little discs. And the ionization process occurs there, and the ions are counted over here on the display. So that's how it works. We have some things up here that we'll be clicking on, our radiation source. So let me pull that up. So you can see radiation source. Right now it says none, which will measure background radiation. Remember, background radiation is low-level radiation that's given off by virtually everything. All right, all matter contains at least one or so radioactive isotopes, so we're giving off radiation in small quantities. We also then have alpha, beta, and gamma sources that we'll be using these three right here. The next column is the barrier. So we're going to do there's going to be a shielding aspect to this where we're going to see how well that alpha, beta, and gamma radiation can be blocked or shielded. We're going to use, well, of course, we have none as an option. We'll do that. And then we have a cardboard barrier, a plastic barrier, and a lead barrier. The number of barriers, pull up cardboard, can go from 1 to 5. We'll be doing a couple of those. And then the count duration will either release radiation for a period of 10 seconds, 30 seconds, or 1 minute. And over here to the upper right is the start count button. So put the barriers back at none. And I think we're going to set that at 30 seconds. But we'll check here with the lab. So as I go back to the lab paper, here. We have some pre-lab questions to answer. What is the purpose of finding the radiation count for each radiation source with no shielding or blocking material? Well, think about that. Before we can test for shielding, we want to see what kind of radiation we get naturally without any blocking, all right? So we want to compare our radiation counts without any shielding at all to see then how effective each shield is in blocking the radiation. What types of barriers are available for use by this virtual online lab to try and block each radiation source? I just showed you that a minute ago, but you can pull it up again on your computer yourself. But there were 3 of them: cardboard, plastic, and lead. Question 3, why is it important to use the same shielding materials, type, and thickness for each of the 3 radiation sources? Well, we want to compare apples to apples, basically, and so we want to compare the same type and thickness of shields for each radiation source so that we can see the differences in how effective those shields are on the different types of radiation, because they are going to be different. Remember, alpha, beta, and gamma particles are different. Right? They have different masses, and that, of course, is going to affect their ability to be shielded. We talked about that in class. So as I go to the next page, let me go to the next page on the board. First thing we're going to do is run our background radiation count and see how much background there is in the surroundings naturally. Okay, so I'll come back over. I'll go back over to my desktop, and you can follow along. So we're going to set up the program. So we're going to set up. Let me pull the lab back up. There it is. It says radiation source none, so we want to make sure it says none, which it does now, and it says background there in parentheses. Type of barrier none. Count duration 30 seconds. So make sure it's on 30 seconds, and then we're going to click on the start count button. Now, I don't know how well you can see it on the screen, but the display is moving. But you'll be able to see this, of course, on your own computer, on your own laptop, or your Chromebook. You'll notice here that these 2 buttons are whited out. I mentioned this on the lab. It says note the whited out buttons will return to regular color once the 30 seconds is completed. That way you know it's done. All right, so we'll just wait here a little bit. Okay, so the color came back to the buttons. Again, I don't know if you can see this on the board, but when I did it myself, my first trial showed a count of 22. So you would write that count down, and then we're going to hit count again, like so, and we're going to count it 2 more times. All right. Then underneath there, under number 1, it says calculate, show work the average background below, and record it above the data tables in both parts 2 and 3. So add the 3 numbers up. You write it down, of course. Divide by 3. You're going to get an answer. Obviously, that's probably not a whole number. If it is, great. If it's not a whole number, then round it to the nearest whole number. We're only going to use whole number counts here. So you're going to record that number, that average background number of the 3 trials, above the data tables in parts 2 and 3. You'll see where that's located. Then you have some questions to answer, 2, 3, and 4. And I'm going to let you do that on your own. Should be able to answer those. All right. And then we're going to go to part 2. I'm going to show you a demonstration part 2. So let's do that. The effective time on radiation exposure. So we're going to set up the program. So let's pull the thing back up here. All right. So we're going to start. We're going to use beta now. So radiation source, we're going to go to beta. Type of barrier none. And we're going to do a 10-second count. So if you look now, we got a little disc right here. It's red. That's beta. and the radiation will emanate upwards from there into the Geiger-Muller tube, and we'll see what happens. All right. So I'm going to go ahead and do a 10-second count. Hit start count. Oh, that thing's moving now. Again, I don't know if you can see it here on the board, but you'll be able to see it on your own for yourself. And so there we go. So my count said 389. Now yours, of course, may differ because it's random. And so our average background count, as I had calculated when I did it, my average 27. I have that recorded up above the data table there. So my actual count of 389, we want to subtract that 27 because the background's going to be there regardless. And so we want to take that out. So 389 minus 27 gave me a count of 362. Okay, so then you're going to reset the timer to 30 seconds and run a 30-second count. Remember to subtract the background from that before you record it. And then you're going to reset the timer for 1 minute and run a 1-minute count. Now, what do you think is going to happen with the numbers? I mean, the longer that counter is counting, what do you think is going to happen to the number? Okay. So then on the next page, we have some questions to answer there, and I think you should be able to do that on your own based on what you observe. All right. So let's go to part 3, and I'll help you get started on that. So here's part 3, the effect of shielding on different types of radiation exposure. So we're going to start with alpha. All right. So let me pull the unit back up here. There we go. So we're going to start here. Our radiation source, change it to alpha. No barrier to start with. 30-second count. And start count. So you see our alpha source there. I don't know if you can see it on your on the board here, but you'll be able to see it on your screen. The alpha count is green. The alpha radiation source, I should say, it's green. And we're getting the count now. And as I flip to the back side of this, where the data table is for part 3. 30-second count, not quite up yet. Okay, and there it goes. So again, when I did this, my count was 1,018. All right. Of course, yours could differ. That's fine, but remember to subtract your average background, which you should have recorded here above the data table. So when I did that, remember mine was 27. When I did that, 1,018 minus 27 gave me a count of 991. All right. So that was with no shield. Then back on the directions on the previous page, it says, next we will look at several shielding barriers and thicknesses. So now we're going to go to a cardboard shield. So under type of barrier, we do cardboard. And then number of barriers, 1. So 1 thickness of cardboard. So now you can see we have a little shield here. All right. Now think about when you get an X-ray if you've had one. So this little shield here is what? Well, it's a little lead covering that you wear when you get an X-ray. So it's protecting the rest of your body. So basically that's what we're doing right here. Only instead of wearing a lead shield like you do at an X-ray, we're going to have you wear a cardboard shield. We'll see how well that works. All right. Count duration is 30 seconds, which it's already set at, and we hit start. Well, I can tell you this. Even with a cardboard shield, the numbers are not flipping nearly as quickly as they did before with no shield at all. So wait here till 30 seconds is up. I'll flip back to the back where the data table is. Still waiting there. on our 30 seconds. There it goes. Okay, so when I did this, my count was 367, which is a whole lot less than 1,018, I can tell you that. Subtracting my background was 27, so that gave me a count of 340, all right? So we went from no shield at or at least I did, no shield at 991 to one cardboard thickness of 340. So you can see any shield is better than nothing, all right? You are now going to repeat that by changing the thickness to 3. We're going to leave it at cardboard. Do the same thing, 30 seconds. And then you're going to switch the barrier to plastic and do 1 thickness and then 3. And then you're going to switch the barrier to lead and then do 1 thickness and 3 again. And that would complete the alpha column in this data table. You are then going to switch to beta, all right, and repeat the exact same procedures with beta. Once completed with that, you are going to switch the radiation source to gamma, and again run through all of the scenarios there, same as before. All right, so I'm going to leave you to that, and then as we after you finish filling out the data table, if you go to the last page of the lab report, you'll see where it says data analysis and conclusions. Let me pull that up. There's that data table that we'll have all filled in. And then the very last page, data analysis and conclusions. Which type of radiation, alpha, beta, or gamma, proved to be the easiest to shield? Look at your numbers, all right? Go from no shield at all to the various types of shields and see how the numbers drop, all right? It says use numbers from the data table as evidence, and based on our discussion of the 3 types of radiation that we did in class, explain your answer. Question 2, which type of radiation proved to be the hardest to shield? All right. Again, look at your data table for the numbers, and then based on our discussion in class of the 3 types of radiation, explain what you saw there. Question 3, compare the mass numbers of all 3 types of radiation, alpha, beta, and gamma. You should know that by now, but if not, certainly go back into your notes and write those down, all right? Question 4, what is the relationship between the size or mass of the type of radiation and how hard or easy it is to shield? This is the telling tale of this lab here as to which types of radiation are easiest or most difficult to shield and why. And why then you should be concerned. Of course, you should be concerned around all of them, but which ones should you be most concerned to not be around? Question 5, which shielding material was most and least effective and why? I think you should be able to answer that too. And then question 6, give an example of a practical application of the importance in shielding regarding our everyday use of radiation. All right, so I think we should be able to answer that too. We've talked about X-rays, of course, already. I think you could use that as a good example. Also, of course, there are other. We use nuclear power as a source of electricity, not only in this country but around the world. So think about how a nuclear power plant is set up and how shielding there protects the general public from the radiation that emanates from those power plants. So you could think about that too as an example. So with that being said, I think the rest of this can be left for you to do on your own. All right. So do it at your leisure. If you're home, of course, if you're in class, you got a time limit to work with. So make sure you work efficiently and get all the numbers recorded, and then you can look at the discussion and answer the questions once you're finished with that. So I think that takes care of it for today. So until next time, this is Mr. Keister signing off. Everybody stay safe, keep working hard, stay focused, and I'll catch you next time. So long, everyone.